Okay, so I have a question for you guys. Given everything you know, and given that DNA polymerase does this, how many reactions can a DNA polymerase catalyze? So I have a reaction here where you're adding an adenine or a DATP to this template. Is that the only reaction it can catalyze? What if it were a G on the template? What would it catalyze? A C. That's a different reaction, isn't it? I mean, if you drew that all out, you'd have different substrates and a different outcome, right? So how many reactions can it catalyze? So 4 is one answer, right? 1 for each nucleotide. But what if I consider what the base is next to it, right? What the primer is part of the substrate. And so here we're attaching it to a C. So you could actually imagine that what you're attaching it to could be 4 different things as well, which if that participates in the reaction, which it does, that's also worth considering, right? Maybe if a C is there, you have a different reaction than if a G or a purine or a pyrimidine, differences. Does that change it? So in fact, you can think of DNA polymerase as catalyzing 16 different reactions, minimally. Okay? And if you want to get really stickly, you could talk about every base upstream for a number of bases potentially impacting the reaction. How many active sites do you think DNA polymerase has? I think it has 4? I think it has 1. So how does it do this? Right? So that's the right answer. Okay? So basically, although it catalyzes many different reactions, it has a single active site. So how does one active site catalyze addition of multiple DNTPs? Okay, because most of the enzymes that we usually think about, if you changed leucine for arginine and you needed to for example, add a carboxyl group in the process of synthesizing those amino acids, you'd use a completely different enzyme to do that for leucine than you would for arginine. Okay? But here, it's a single enzyme that does all of that. So how does that happen? The simple answer, the way I like to think about it, is that the polymerase works by Braille. Okay? It doesn't actually care at all what nucleotide it's adding, and that's because of this property. Okay, so this is the structure of DNA. I'm not going to go through that in detail other than to point out that this structure is very regular, and it doesn't matter what each base pair, which would be these blue regions here, is, it looks the same. There are subtle differences, and if you really get down to crystal structures and things like that, there are minor differences. But in general, the structure is very similar, and that's because the base pairs that make up the 4 different types, so TA, GC, AT, and CG, have the same structure is one word, but the same dimensions is even a better word. Okay? So the distance across here is exactly the same for all 4 types of base pairs. The way the different elements of the DNA or the nucleotide are placed is exactly the same for all 4 nucleotides. And this is actually critical for allowing a single enzyme to do all of these different reactions. Okay? So what I want to illustrate here is the basic principle of how this works. So when you have the nucleotide, remember I told you the nucleotide has to base pair in order for catalysis to occur. And so the concept, and this has been demonstrated by actually crystallizing these various intermediates, is that when you base pair correctly, what you do is you put this triphosphate group in the correct position so that this primer, 3'OH, can do, for the most part, what all chemical reactions in the cell are, a nice SN2 nucleophilic attack, attacks this phosphate, kicks out the pyrophosphate, and can move on. Okay? If you try and put an adenine across from an adenine, even though it will have some affinity for the binding pocket, it will not be able to put that phosphate in a correct position so the hydroxyl group can attack it. Okay? And where it is going to change depending on what type of mismatch you have, but none of the mismatches will put it here. Okay? And this is very stylized. This is not actually what it looks like in the enzyme, but it is exactly how the enzyme works. Okay? So the reason you require base pairing is because that puts the correct components for catalysis, most notably the alpha phosphate and the 3' OH, in the correct position for them to act. So the key things here are base pairs have the same dimensions. Okay? And correct base pairing places the 3' OH proximal to the alpha phosphate of the DNTP. Okay, so that is how the cell manages to make that work correctly. And basically, the more this is wrong, the slower the reaction occurs. Okay? So, and we'll talk in a moment about how you can get it sort of right, and you can actually make a mismatch happen. But in general, the rate at which this reaction can occur is so slow that by the time it might actually occur, this mispaired nucleotide will simply float out of the active site. So the very low affinity it has without the base pairing is not sufficient to keep that nucleotide in the active site long enough for catalysis to occur under those circumstances. Okay? Whereas a correctly matched base pair not only will be bound more tightly, but will be put in such a position that the reaction will go much faster. So there's both a temporal and an affinity mechanism to make sure the correct reaction occurs.